Hello. We'll just reintroduce ourselves. I'm Tebe, and this is
Shiva.
And so the title of our presentation is Solar Suitcase Energy Storage System.
And so when we began looking at this competition, we tried to determine what it was that we would need to improve the overall system, like what it is that limits its ability to be used on a daily basis for third world hospitals. So we decided to analyze the storage system because the storage system affects the portability of the solar suitcase. It affects its capacity, the amount of appliances you can connect to it. It affects its overall life of the system and its reliability and efficiency. And so we began by comparing various chemistries.
So initially, we immediately thought of lithium ion, just because that's the big battery type chemistry that's out right now. And so here's just a brief chart of some of the comparison between the two. Basically, energy density, cycle life. Like before, he talked about portability. So lithium ions have a higher energy density. So for the same, say, amp hours, wattage or like capacity, you can have a smaller battery. We compared cycle life, charge time. Charge time for lithium ions is like 4 times faster, 4 times shorter. And the cost is for the same wattage, so for the same capacity, it's 4 times more expensive for lithium ion. But the cost per cycle turns out to be 4 cents more expensive for lithium ion, just because it has a much larger cycle life. So you can go through much more cycles before, like I guess the density would be unusable, like the capacity.
So when analyzing lithium ion and trying to integrate it into our system, we decided, well, we had to first look at the parameters and certain specifications of the chemistry to follow in order to integrate it into our system. So after doing research, we determined that we would need to look at constant voltage. We would need to maintain constant voltage while charging. We would have to limit its charge current. We would also have to monitor the temperature of the lithium ion cells, as well as limiting overcharge, because that could lead to potential health hazards if lithium ion is exposed to the environment. So now the question was, how do we incorporate this into the solar suitcase design?
So initially, we considered using the existing charge controller that was given to us in the solar suitcase, but it turned out to be impractical because the hardware and the software is proprietary, owned by the company, and it's unlikely they'd even give us access to try to tinker with it. And another issue was that when they designed it, they probably designed it initially just for lead acid type batteries, and so it might be very difficult to try to convert it to charge a lithium ion or even say any other type of chemistry.
And so we came across the free charge controller project. What this is an open source hardware and software project that it uses solar power energy to charge whatever batteries. So this we found online, and it's a flexible design. It incorporates a microcontroller, which allows for customization. Basically, you can have any type of power source or even chemistry type, depending on the software you load on. So as you can see, it says we can charge lithium ion, lead acid, nickel cadmium, nickel metal hydride battery types. It has a large development community, about approximately 130 people working on it, all volunteers. And so we realized that this open source project may be a perfect application for a solar suitcase.
Yeah, because it kind of fits together. They're both kind of open source projects. Also, this has the members, a lot of them are from industry. So a lot of new members come on and they work for a lot of technical companies. So they're looking to use this for their own kind of applications within their own companies, or I guess as side projects. So we tested what we did was we tested the original charge controller because we were trying to figure out how it charges and everything like that, how it worked. One thing we figured was that it has a 92% efficiency, which a group member of us tested, but he's not here. He basically compared the input and output currents because the voltages were the same, and so basically based on the difference or like the relationship between them, he figured out that was 92%, and this is tested by us. The free charge controller is this piece-by simulation that the creator of the group did. So he's simulated at 93%, so we don't know actually what it would be in like a real life situation.
However, like in the simulation, they incorporate the loss from MOSFET and the overall buck circuit that was used. So what wasn't incorporated was like the microcontroller power consumed by the microcontroller and the power circuit, which would be minimal in comparison to the buck circuit. So that would be a pretty accurate simulation of efficiency.
And currently, their current design, I say for a typical board, has a rated power of 192 watts, which we got from the fact that they both can go up to 24 volts, but this one is limited to 8 amps max current, and the ProStar has a 30 amp max rated current. The cost for this one is slightly more expensive, but it is slightly more flexible. So in terms of flexibility, it's modular because what you can do is you can add up to 3 boards, as in daughter boards, and each of those boards will carry 8 amps, so you can go up to 32 amps in a system. You only need one microcontroller, which would be on like your motherboard, and then so that would reduce the cost of each of the subsequent boards. You just need a buck converter on each board to handle the 8 amps. So it makes it easy to design it towards whatever kind of application you need, the power requirements for the system you're trying to design. And it's also very easy to access. In terms of the board design, it's very easy to get access to pins to test currents and voltages, or maybe data transfer between the microcontroller and your computer or anything like that.
The board itself includes like extra pins so that you could put more test pins or whatever else is needed to analyze the data, like you said.
In terms of reliability, I know the ProStar is rated for 15 years, they say. For the free charge controller, we don't know what the reliability is because it hasn't been tested yet. But the guy who created the group, Chris Tutner, is a reliability and test engineer in his day as a profession. So eventually, he said he would work towards kind of testing that board out in, I guess, temperature chambers and everything like that.
So, the future improvements and testing for this board would include a mechanism that can do quick charging for various types of chemistries, and this would be done through software. So a lot more research would have to be done or work into creating software that could implement various chemistries at once. So maybe by the turn of a switch or some sort of mechanism that could adjust or change on spot the chemistry
which
type
chemistry you want to charge. Because right now it's limited by the size of the onboard memory on the microcontroller. So you can only charge when you load your software on, you have to compile for one single type of chemistry. So you load on lithium ion chemistry, and you not include the other files that can charge silicic acid or the other types of chemistries. And so if you want to charge different chemistries on the fly, it's not feasible. Someone has to come with a computer, recompile the code, and then load it back on, which, I mean, where this thing is being planned to be deployed is not going to happen. So like a quick thing we're thinking is just some way of being able to switch between it very easily. Also moving towards expanding the current for each board, because using like 4 boards together is very big. It makes the system very big. So if you can have a single board that can go up to like a current that you'd like, then that would be beneficial if you make it smaller. I know currently they're trying to push towards 20 amp board from an 8 amp. Also right now it doesn't have any user feedback. So here we have a whole bunch of LEDs that he showed to us earlier. It gives feedback on like the LED, like the panels, how much dust has been collected. Right now there's no feedback. On the ProStar there is feedback on basically if you're full or medium charged or empty, and so that tells you something. Here there's no feedback. One of the things they're trying to do is add so you could put an LCD display. Not that you'd always have it, but just in case you had it, you could easily read like current and voltage levels and stuff like that.
So like in the application of a rural area, it could be on board, like everything could be read, analyzed. You wouldn't have to hook it up to a computer to access.
1 minute.
Alright. So that basically sums up.
But tests for reliability have to be done. Like right now, we have no information about this. We don't know how it operates in operating temperature ranges and over like its rated current and voltage ranges. We don't know how it's going to behave. We also haven't done tests yet on each kind of battery, like how it charges it. Does it charge it correctly and everything like that? I mean, we basically just got the board completed like a couple of days ago because it took so long for the hardware to come. But like, yeah, so in the future we have to do a whole bunch of tests to make sure that it actually is functional and that it'll work. I think that's it for us.
Yeah.
Any questions?
Thank you.